All right, so if there were to be a power outage for a prolonged period of time, name some of the items that we would no longer be able to use or access. And you can either type it in the chat or you can come on mic. Anything you can think of that we would not be able to use without electricity. Somebody, anybody.
Air conditioning, like
Yep,
in the house.
yep, that's correct. Anybody else? All right, so in addition to air conditioning, we wouldn't really have um, access to fresh food that our refrigerator or freezer would provide to us, um, stove, oven, microwaves, charging of your electronic devices such as your laptops and your cell phones and your tablets and all that good stuff. All right, so without power, most of the devices that we use today, we wouldn't be able to use. All right. So in order to understand what's occurring with electricity, we have to look at the base unit of particles. Okay. So this is the electron theory of charge. So the base unit of matter is the atom. And the atom is made up of electrons, protons, and neutrons. So your electrons are negatively charged, your protons are positively charged, and your neutrons have no charge. All right, so they're neutral. Right? So the atom is considered to have a dense center part. That's what we call the nucleus. And then the electrons and the protons, have the property called charge. So again, electrons are negatively charged and protons are positively charged. All right. So the same thing I just went over. Your electrical charges, they interact to produce electrical force. All right. So if you've ever heard the saying opposites attract, this is based on science. So if you have a electron and a proton, which one is negatively charged and the other is positively charged, they are actually attracted to each other. There is a fundamental electrical force between those two opposite charges. All right, so that's where you hear opposites attract come from. So your like charges, if they're both positively charged or both negatively charged, those like charges will repel each other. So they'll try to go in the opposite direction of each other instead of attract towards each other. All right, so electrostatic charge. This is an electrical charge that's confined to an object and it's not in motion, so it's not moving. All right, that's what static means. All right, it means it's stationary, not in motion. All right, so your electrostatic charge is your electric charge that's confined to an object and it's not in motion. All right. All right, we also have electrical conductors and simulators. So your electrical conductors, these are your metals. All right, so this is what the electrons are used to move through. All right, so if you've ever had a charger that you had to plug your device into the wall outlet for, inside that little plastic, circular part of the charger is metal. All right, so that rubber part is pretty much insulating the metal inside so that don't electrocute yourself and whatnot. All right, so most of the metals that are inside of these charging devices are usually copper. All right, so also in addition to conductors, we also have insulators. So here the electrons are not as free to move throughout those materials. So your insulators, these are materials that we use to um, insulate temperature, to construct buildings and things of that nature. So your wood, your plastic, your rubber, your glass, all of that is a form of material that is served to insulate or protect you from the elements. All right, so a semiconductor, this is in between a conductor and a simulator. So it's a third class of materials. Examples are silicon and germanium. All right, so sometimes they conduct and then sometimes they insulate. All right, it just depends on the conditions and how pure they are. Okay, so silicon and germanium, this is these semiconducting materials. These are used in some of the devices that you use every day, such as your phone, and your laptop computers. All right, so again, between those electrical charges, you have force fields. Now, a force field is the field surrounding the charge. All right, so for electrons, the field is moving inward towards the electron, the negative charged particle. And then your proton, the field is moving outward away from the positive charge. Right, so charges produce force fields in the space that surround the charge. All right, so that's why they call it an electrical field. All right, so your charges have electrical units to them. All right, so your electric field is represented by drawing of lines of electric force or field lines that show the direction of the field. All right, so again, electrons, the direction is inward towards the particle, and the proton is directed outward away from the particle. So by convention, the field lines, when they're closer together, that means the electric field is stronger. And then if they are further apart, if those field lines are further apart, that means the field is weak. So the more lines you have, the stronger the field. The less lines you have, the weaker the field. All right, on to current and resistance. So the flow of charges, this is what we call an electric current. All right, so the electric current is the flow of electric charges over time. The more charges you have, the larger the current will be. The less charges you have, the smaller the current will be. All right, so the flow of charges, think of it as like, the flowing of water through some sort of streamline or stream or river. Okay, these charges are moving in a certain direction and they're all moving simultaneously. All right, so materials have a property of opposing and reducing current. This is also called electrical resistance. So resistance is a form of friction. Okay, so let's say you're driving in a car right down the street and you see a stop sign. So all of a sudden you need to apply the brake, right? That brake is applying friction to your car in order for it to come to a stopping point. Okay, so that's what friction does. It opposes the motion of flow. So instead of going forward, you're slowing down or you're coming to a complete stop. Right, so brakes on a car is friction. So think about resistance within the wire, slowing down the current of flow for the charges from the wall to your device that you're charging. So from the outlet of the wall through the wire, there's some sort of resistance. And it all depends on the materials that you're using. Mostly used is copper because it's relatively cheap, but they are using other metals as well. All right, so resistance is a form of friction within the wire opposing the flow of charges, right? So the charges are in motion and the friction is called the resistance within that wire. All right, next we have magnetism. All right, so the Earth has a natural magnetic field. Magnetism is due to metal, mostly iron. On the bottom left, you see a picture of magnetite. So this is like an iron element. And here you see a paper clip that's kind of sticking to it. So if you've ever played with magnets, depending on whether it's on the positive side or the negative side, sometimes you'll have a force pulling it together, and sometimes you'll have a force pushing it apart, depending on which part of the magnet you have facing towards the other magnet. All right, so our geographic North Pole is the magnetic field's South Pole. And our geographic South Pole is the magnetic field's North Pole. Okay, so it's kind of opposite of what we're used to. So the magnetic field has a north and a south pole, and it's opposite of our actual geographic north and south pole. All right, so again, the flow of charges goes from positive to negative. So at the positive end, you have the electric field flowing outward away from the charge. And then for the negative part, you have it flowing inward towards the charge. All right. All right, so this picture right here is a horseshoe magnet. All right, so the North Pole, this is the proton, so the charges are, the electric field is pointing outward away from the charge. And then our South Pole is the electron, negatively charged particles, and the electric field flow is inward towards the negatively charged particles. So the flow between positive and negative is outward from positive inward to negative. All right, that is the magnetic field horseshoe magnet illustration here. So the flow between positive to negative is from positive to negative. All right, so your magnetic fields, these are formed by moving charges, and they affect moving charges. All right, so again, our geographic North Pole is the Earth's natural magnetic field's South Pole, which is negatively charged. So you see the electric field line arrows pointing inward towards the North Pole, our geographic North Pole. All right, so that's negatively charged. And then the proton, which is the North Pole magnetic field, but the South Pole geographic field, pointing outward. All right. So from positive to negative. All right, so magnetic forces can accelerate charged particles by changing their direction. And magnetic forces can also cause charged particles to move in circular or helical paths, right? So if we go back to that prior image, all right, this is a circular motion here. All right, so from the positive part of the magnet field in towards the negative part of the magnetic field. All right, circular or helical motions. All right, magnetic forces cannot change the speed or kinetic energy of charged particles. All right, so earlier this semester we talked about speed. This is the distance covered over time. All right, so this is just a scalar quantity, a numerical value of how fast you're going. The kinetic energy, this is the energy of motion. Don't forget, kinetic energy is represented by KE, and it's equal to 1/2 mass times velocity squared. Magnetic forces cannot do work on charged particles. If you guys remember, work is force exerted over a certain distance. All right, so magnetic forces cannot do work over certain distances on charged particles. It can change the speed, but it can't do work on that charged particle. All right, so here's another illustration. This is the magnetic field bar. So again, you have outward flow from the North Pole to inward flow towards the South Pole, which means our North Pole is positively charged and our South Pole flow is negatively charged, right? Because it flows from positive to negative. All right, so unlike poles attract, so opposites attract, north and south, south and north are attracted to each other, but like poles repel. So north and south are going in the opposite direction of each other because they repel each other.